Most students learn polynomial division as a series of steps to follow inside a long division bracket. To understand the logic behind those steps, we have to look past the bracket and focus on the structural manipulation of the terms. This is the degree constraint, the mathematical requirement that determines whether division is even possible. Here, the variable m represents the highest degree in the numerator, and n represents the highest degree in the denominator. If the numerator's degree is strictly less than the denominator's, the operation halts. Division cannot proceed. This rule applies across every level of complexity, from dividing by a constant to a single variable monomial, and eventually to multi-term polynomials. This constraint dictates the endpoint of our work. It tells us precisely when a division is complete, and by extension, it defines the structure of the remainder. To see this constraint in action, we begin with the simplest environment, dividing a polynomial by a single monomial. Take the expression 3x squared plus 4x plus 3 divided by x. We resolve this by distributing the denominator across each term in the numerator. This breaks the fraction into 3 isolated components, allowing us to evaluate the degree constraint for each part. The first 2 terms simplify into 3x and 4. Division succeeds here because the numerator degrees are either greater than or equal to the degree of the denominator. In the final term, 3 over x, the constant has a degree of 0, while the denominator has a degree of 1. Since 0 is less than 1, the division must halt. This specific term cannot be simplified further, making it our remainder. When we change the divisor from a monomial to a binomial, the distribution becomes more complex. We need a way to find the denominator inside the numerator. Here, we are dividing 3x squared plus 4x plus 4 by x plus 1. Our strategy is to actively manipulate the numerator until the denominator appears as a factor. To do that, we focus on the middle term, 4x. We need a 3x to pair with our 3x squared term. That specific combination allows us to factor out the x plus 1 we're looking for. So we split 4x into 3x plus x. By grouping the 3x squared and the 3x, we can factor out the x plus 1 and cancel it against the denominator, leaving 3x. Polynomial division is an act of reverse engineering. We are splitting terms to force the shape of the denominator to emerge. As the degrees of the polynomials increase, we have to be more precise with the structural alignment of the terms. Take this degree 4 polynomial divided by a quadratic. If we look at the numerator, there is a gap in the descending order of the degrees. The sequence skips from x to the 4th down to x squared, leaving the x cubed step empty. We insert 0x cubed as a placeholder. This preserves the structure without changing the mathematical value of the expression. With the alignment corrected, our goal is to eliminate the leading term, x to the 4th. Acknowledging these ghost terms provides the necessary scaffolding for the math that follows. To eliminate that leading term, we use a technique called algebraic compensation. We start by determining what we must multiply the divisor by to match the leading x to the 4th. In this case, multiplying the divisor by x squared gives us x to the 4th plus x cubed plus x squared. We place these new terms directly into the numerator to create a factorable block. By inserting these terms, we have changed the value of the numerator. To maintain equality, we have to account for that change. We compensate by immediately subtracting the exact terms we just added. This keeps the equation balanced. Now we can extract the factorable block. It cancels with the denominator and leaves x squared in our quotient. The remaining subtracted terms combine with our original numerator to form a new, smaller expression. We check the degree constraint again. Since the numerator is degree 3 and the divisor is degree 2, we repeat the cycle. Algebraic compensation is a continuous cycle of forced borrowing and immediate balancing, driven by the requirement of the degree constraint rule. The process iterates, systematically removing the x cubed term and then the x squared term. Once all cycles are complete, we are left with this final result. The expression is now split between a clean quotient and an unresolved fraction. Now we perform the final degree constraint check on the fraction. The numerator has a degree of 1. The denominator has a degree of 2. Since the numerator's degree is lower than the denominator's, the halting condition is triggered. Algebraic compensation can no longer proceed. This indivisible fraction is the definition of a remainder. Polynomial division is a logical process of structural term matching. The calculation only concludes when the degree of the numerator falls below that of the divisor, reaching a point of mathematical exhaustion.